Alright, hey guys, what's going on? So today we're going to be talking about the Ruse-Lanczos equation in GR. So this is a very interesting object in GR, and it's going to help us understand something about the nature of tensors that have symmetries that are very similar to the Riemann Curvature Tensor, and it's going to introduce to us ideas on how we can integrate this into complex numbers as well, or these tensors, and make them complex. Okay, so if you like this kind of content, if you're getting the pattern now, I'm releasing GR videos on Mondays, quantum gravity videos on Wednesdays, and then Fridays I'm still thinking about what I want to do there. And if you want to support the channel on Patreon, you can get notes there. If you want to become a member, you can get member-only content and early content as well. And so with that being said, let's get straight into the topic. So today we're talking about the Ruse-Lanczos equation. What I want to do is once we're done here, we're going to talk a little bit more about complex tensors, and then in our next video, and then what we'll do, excuse me, is move on from. So we've talked about E&M. We've talked about conformal field theories in GR. We're going to move on to some actual physics, right? And so the actual physics is going to be finding solutions to the Einstein field equations and so forth. Okay, that's a little bit of a divergence, but let's talk now about the Ruse-Lanczos equation. So consider the 0-4 tensors satisfying the symmetries similar to those of the Riemann Curvature Tensor. Alright, so these are those symmetries. I won't go through them again in detail because we've already talked about them. But when we saw when discussing electromagnetism that for the tensors of this type we can construct right and left duals. Okay, so we have our right dual and we have our left dual, and we can calculate these guys with this Levi-Civita symbol. Okay, and we can also raise a few indices with our metrics. And when we do that, we get these two guys here, okay? So, and we could, so the right, or this is the left dual, this is the right dual. The left dual is going to raise, we have, this should be a mu, right? Mu, no. So, we have mu nu, we're keeping these down and we're raising these two guys, right? We're raising those two guys. Okay, and then, so this should be a mu. And what we, so here we're doing the opposite, right? We're raising the left two, okay? So we're not going to go back into the details of these tensors, but we are going to rely heavily on them. So if you want a refresher on these, you can go back a few videos and look at the E&M stuff when we introduced this. So double application of the right dual, okay, is going to be this guy. So we have two applications of the right dual operator, and what happens is, okay, so this is we right dual and then we're going to right dual again. So that's what we get down here, okay, and then this identity here, this 1/2 times 1/2 gives us 1/4. Then we have an identity here where, and I'm realizing right now that we have, let's see, sometimes when I type this stuff out, it doesn't copy the way I want it to. This is tau sigma, this is going to be kappa lambda, and then this guy was just an extra piece. Don't need that. Okay. And so we get this relationship here, right? So this is something that we've worked out before also when we looked at these tensors, or this application here, and then we get to this point, right? So the right dual, or the right dual applied twice, so the double right dual, if you will, is equal to this, okay? We can see that from the application of symmetries of this tensor, we can get that the application of the double dual gives us the negative of the tensor back, right? So we have, so from symmetry, right? So we take this guy, right? So we have kappa lambda. So we flip-flopping these two guys, which is why we get this negative down here. And we can do the same thing for the application of two left dual tensors, okay? So, we have these two guys, okay? So, now let's calculate this thing, right? So we're applying the left dual and the right dual, and so what we get there is left dual, right dual, and here's our beginning matrix. So we get this and this, and we get this in here. So we need to calculate this, okay? And so when we do that, we get a lot of stuff, because when we did it up here, we were able to, we have rho sigma, kappa lambda, and then tau phi, right? Here, nothing's really contracting, right? We have rho sigma, no rho sigma here, kappa lambda, no kappa lambda here. So we need to really flesh this thing out, okay? So to do that, I'm going to try to go through this fast. You can pause the video if you want, but this is just a side calculation that we need to do to get us to the place we want to get to. And the place we want to get to is going to be, I'll just skip ahead really quick, right here. This is our Ruse-Lanczos equation. Lanczos equation. But with that being said, let's go through this. So this thing can be fleshed out into a determinant, okay? Let's just forget this part. We're going to go straight into the determinant. So this here is a determinant of all this, okay? And so we can, okay, we'll flesh this out, right? So this is here, this is here. I'm realizing some of these are, when they copied over, should be kappa, and then we have kappa, right? So all of this, and then, right, so this should be a kappa, not a big K. Kappa. And then we do this even more. We flesh things out. This, we find the determinant of this is all this, the determinant of this is all this, and so forth, okay? So this is just me. This is really just for my own edification. I want to minimize assuming things as much as possible. Again, you can pause the video, and you could check here as well if you want to. But this is just one ugly step to a final destination that is going to be not as ugly. Okay, so just taking the first parentheses, we're going to calculate its product with the W tensor in our formula for the right and left dual tensor. And so this is the first, this is just this one right here, right? So if we go down here really quick, just this guy up here, okay? We're just going to deal with him for right now. And we have all of this in here, okay? And what we can do is we can say, well, we can swap some things. We're going to have to, when we swap, we're going to have to make it positive. Or we're going to have to swap the sign, right? So this just means I'm swapping the sign. And so when we do that, we get this here, all right? And so, I'm realizing right now, we can swap the sign. We could swap the sign here as well. So the point here is that this guy, these two guys here, will give this, and then these two guys here will give this one. All right. Okay. So recall that the W tensor, we're demanding to have some symmetries, right? So we have this thing here. Now we can deal with its symmetries, okay? Symmetries are this, okay? And so we're still focusing on the first set of parentheses. Again, just this guy right in here. Just focusing on him. Then we get this right here, okay? So all of this gives us this, right? So this is to say that this reduces down to this, because we have complete contraction. Some places we have contraction, other places, right? So we have lambda nu, and then kappa mu right here. So, and then kappa mu here as well. So, doing the same thing for the other three parentheses, we get these, right? So, I'm skipping over some steps, right? Because a lot of this is just really boring calculation of a determinant of a bunch of Kronecker deltas. So I'm kind of punching to the chase here and giving you the answers, okay? If you want to, you can go through the math yourself. I didn't really deem it quite necessary to go through all of the math and present it here because that would just be super boring. But this is what it all comes down to. So putting all these together, we get this here. Okay? These two guys here contribute to this one. These two blue ones contribute to this blue one. These two green ones contribute to this green. Red contributes to these. And then the orange to this one. Alright, so therefore the left-right dual tensor, which is this guy, again, this is what we're calculating up here, right here. The left-right dual tensor is this in here. Rearranging this, we get we finally come to the Ruse-Lanczos equation. The Ruse-Lanczos equation looks like this, right? So what we're doing is we are saying, so we have this guy here, okay, and then we're multiplying a bunch of stuff out. If we multiply this out by this, well, we get this guy, okay? So I'm tracking just one of the metrics. This metric here is going to be this metric here, right? Because it's multiplying by our W, along with the kappa mu, along with that kappa mu, okay? And it's also multiplying by our 0-2 tensor W, okay? So that's this guy right here. And you could see how this works out for all of these, okay? The Ruse-Lanczos equation reveals the relationship between the left-right dual tensor and the original tensor. So we can simplify this equation if we want to invent a new tensor. And that new tensor is going to be this guy right here. Alright, so this is interesting. This looks an awful lot like our G mu nu, our Einstein tensor. And we'll get to that. Okay, this is actually quite interesting. So in this case we can write this is equal to all of this then, right? Because this is a p tensor, this is a p tensor, another p tensor, another p tensor. So that's all of this. Recall the definition of the Einstein tensor. Okay, now I'm alluding to the Einstein tensor. The Einstein tensor geometrically we came to the understanding that geometrically the Einstein tensor was part of the Riemann tensor that lied on the plane tangent to a point on a manifold at some point, okay, or at that point. We could see that since the p tensor takes the same form, we can say the same thing about the p tensor. However, this gives us something of a geometrical interpretation of the left-right dual tensor W. Okay, so what exactly is that, right? So we have this 1/4 here. It's a little bit different. But suppose this is just a number, right? This is just some factor. So it's not directly really related to the tangent space on some manifold, but it looks an awful lot like it, so we might be able to think of it perhaps in that way. Okay. So here we are. This is our left-right duality side of the equation. These are our projections. Okay. There are projection tensors with the metric. We can see that when we add the left-right dual tensor, we get the Kulkarni-Numitsu product of the projections of the Riemann tensor with the metric. So in some sense, the left-right dual tensor is related to the projection of the Riemann tensor to a lower dimensional tangent space. To compact things more, we can write it in this way. So the Kulkarni-Numitsu product is really, this is the product right here. It's a product between some arbitrary tensor with another arbitrary tensor, typically the metric tensor. Okay. And you can see, if you look carefully at this thing, we have lambda nu, lambda mu, and then kappa mu, kappa nu. So you can see some patterns in here, and then we have kappa nu, kappa mu, lambda nu, and lambda mu. So this is that product. This is the product between P and G. And one way to write this is P like that. Okay. So these two guys actually I'll do it like this. These two equations are equal. Okay. So it's natural to think that we can apply this left-right duality to different parts of the Riemann tensor now, which is going to be the topic of our next video. I don't want this to be too long, but this is going to dive us into something really quite interesting about complex 0-4 tensors. Okay, so recall that we decompose our metric into three different parts. Right, so this is our Riemann metric. Then we had our Riemann curvature tensor. Then we had the Ricci curvature tensor, the scalar curvature tensor, and the Weil curvature tensor. Now that we've talked about the Weil curvature tensor, we're ready to talk about what we can do when we take the left-right dual of each and every one of these, and what the left-right dual in each and every one of those geometrically sort of gives us. Okay. So with that being said, this is somewhat of a shorter video. I prefer to break things up just because I don't really like doing really long videos. So yeah. So with that being said, I hope you guys like this kind of content. Make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel and get notes. Again, if you become a member, you can get videos early. You can get member-only content as well. And with that being said, I'll see you guys in the next video. Bye.